Hello physics students. In this video, you're going to learn about something called total internal reflection and critical angle. Now this isn't just some abstract idea that you're learning about in a physics class. If there wasn't total internal reflection, right now you probably wouldn't be able to watch this video. So let's take a look at what it is. What I have here is the optics tank, obviously that I used in the refraction video, and you could see the light refracting as it goes from the water to the air. And I don't even need to ask you because you could see it. You could see that the light is bending away from the normal. Remember, the normal is right here, perpendicular to the surface, and the light comes in something like this, and this is where the normal is, and it bends away from it slightly and continues on. But also, as I mentioned in the last video, some percentage of the light reflects. So you always get that when there's refraction, there's some bit of the light, some percentage, maybe it's only like 10% or 20%, but there is a little bit of light reflected. Now as I increase this angle here, this is theta 1, which is smaller than theta 2. That's another way to say light bends away from the normal. But as I increase theta 1, I also increase theta 2, as you could see. And that can keep going, and then this light, because this angle is getting bigger, the light in the air is getting closer and closer to the surface of the water. Now, if we were in class, I would ask you, what is this angle getting closer to make sure that you don't say it's getting closer to 0 degrees, thinking that the angle is measured with respect to the surface. Again, it's measured with respect to the normal, so the angle is getting closer and closer to 90 degrees over here. But if I go too far, what happens is, the light refracts very near the surface, and if I go any more than that, it can't refract anymore, and then 100% of the light stays in the water. We get what's called total internal reflection. 100% of the light, this surface up here is acting like a perfect mirror, reflecting 100% of the light. And if I keep increasing, I get total internal reflection for anything greater than this little, what we call a critical angle. So let's suppose the critical angle here is 50 degrees. Anything beyond 50, 100% of the light's stuck in the water, okay? But I also, before I move on, want to emphasize, or I should say, I just want to tell you that this can only happen when the light begins in the higher index, in this case, the water. You cannot get total internal reflection starting in the air and going to the water. Let's take a look. So here, no matter what angle I make the light come in the air above, you could see that always some light gets through. And the reason why is because the light will always bend towards the normal, not towards the surface. So you cannot get that case where the light reaches the surface and then beyond it, all of it reflects. Again, total internal reflection, you have to begin in the material that has the higher index for it to be possible. Okay, so let's go to the board, summarize with some notes. So here's a diagram summarizing what I did with the water tank. I've got a surface here, and this time I chose to have two different substances other than air and water because you could have total internal reflection with any two surfaces provided that we have one index higher than the other. So in this case I picked alcohol, there's the index, you could find it on the reference table if you wanted to, and zircon 1.92 also on the reference table. We saw that in the video, yesterday's video. So here is the ray 1 that I originally showed. It comes in, bends away from the normal, and then when I increase this angle to another second angle, this ray up here got closer to the surface. And if I keep increasing, what happens eventually, I get to this critical point where the light would refract along the surface, but it doesn't. Instead, it reflects and we get 100% reflection. And then if I go to a ray even a greater angle here from the normal, again, 100% reflection. For any ray coming in these range of angles, 100% of it stays in, none gets into the other surface or material, alcohol. So rays 3 and 4 experience what we call total internal reflection. Let me create a pause to allow you to copy these notes down. All right, so the next thing, can we calculate this, what we call critical angle. By the way, I should have mentioned this is a theta with a subscript C to denote critical angle. Can we calculate that? Yes, we can. So that's the next phase here. Calculating the critical angle for this alcohol-zircon boundary. Again, a note emphasizing the light must start in the zircon because it has the higher index. So I draw just a quick picture here. I don't need to draw all these rays, just the critical one that would have refracted along the surface like this. And so we put the indices. This is unknown, and the second angle in the lower index is always 90 in these critical angle calculations. But we begin with Snell's law. This is again on the reference table. I don't need to go to the screen to show you that because we saw that in the last video. I plug in, again, material 1 is the zircon, the higher index, with the unknown critical angle. And on this side, 1.36 and 90 degrees. And there's all my data plugged into the equation. Again, don't forget the degree sign. You lose 1 out of 2 points on the Regents. Divide both sides, but because we're solving for this, divide the 1.92 to the other side. This times that divided by 1.92 gives 0.708. So to get the critical angle, I have to take the inverse sine of 0.708. I ran out of room here, so I tucked this over here. But on your notes, you could put it underneath to make it all look nice and neat. So there's the critical angle between the zircon and the alcohol. So go ahead, take a moment, and write those notes down. All right, now, at the start of the video, I said, if it wasn't for this phenomenon, you wouldn't even possibly be able to watch this video right now. So why? How does critical angle right now help you as you're watching the video? So what I'm going to do is reconfigure the camera to show you a little demonstration. So give me a moment. So you've probably heard the term FiOS internet, and what that is it's fiber optic internet. And what they're doing to transmit the internet that you're using is they don't use electricity, they use light. In fact, they use laser light to flash a certain signal, and then that flashing pattern you could decode as an internet signal. But if you think about that, that's kind of an odd choice to transmit internet. Say you want to transmit internet from one coast to another, say California to New York, and if you're using laser light, well, maybe there's mountains in the way, or maybe as the laser light is going, a plane flies by and interrupts the internet signal. So how do they send the internet across the country with a laser? They use these things called fiber optic cables. This is an actual fiber optic cable. So it looks like hair, but it's plastic. And I'll show you what it does by just taking one of the lasers. The green light works the best. And I'll shine it into these little hairs at this end. And what you should see is that at the other end, you see the light flashing on the right side of the screen. And so somehow this light is going around and spiraling around this spool over here and coming out the other end. The light is going around corners. And so that's what we're going to be studying in a moment. What it's utilizing is total internal reflection. The light gets trapped inside this plastic. And maybe it'll look a little more dramatic if I move the original laser off the screen so that maybe the flashes at the end there will be brighter. Well, anyway, you get the idea. Now, how does this work? I'll explain on the board in a minute, but first I want to show you this here, this plastic coil. It's a model of a fiber optic cable. It works the same exact way. You see that there's a straight portion here of plastic, and then it spirals around and it comes up like this. So you'll see that the light ricochets around this pretty dramatically with the laser light. I will start with red, which was giving me a little trouble. There it is. Looks very beautiful. You see the light sort of, as I move the laser around, it's ricocheting around this tube, stuck inside, ricocheting and coming out the end. Again, if I flash, and I could do like Morse code or something like that, or something more sophisticated for an internet signal, trapped inside. And then I'll try the blue light. You see, that looks very beautiful too. Pretty dramatic. As I move it around, you could actually see the light ricocheting around in that plastic tube. Again, total internal reflection. It's trapped inside. I'll explain in a minute. And then the green light. Oh, that's very bright. And again, you see the ricocheting around, stuck inside the plastic tube, comes out the end over there. All right, so let's go to the board to summarize how this works. So let's take a look at the physics behind those beautiful demonstrations. So I have some kind of optically dense material here, like a piece of plastic, and it's curved around a corner. I take light here, and the light does not 100% reflect here because I'm going from air into the plastic, low index to high index. You cannot have total internal reflection. So the light instead just bends towards the normal and goes in. And then when it strikes this surface, what happens, because it's like a glancing intersection with the surface, this angle's large. In fact, it's larger than the critical angle. So no light can get out and refract away from the normal. 100% of it reflects like this. Same thing here. This is greater than the critical angle. So none can refract away from the normal. 100% reflection. Again, greater than the critical angle, 100% reflection, 100% reflection. So at all these angles, theta 1, theta 2, theta 3, and theta 4 are all greater than the critical angle, so light can't escape. However, at the end, notice this is coming in like really almost perpendicular to the surface. In other words, the angle of incidence is pretty close to zero, or getting close to zero. It's small. The point is that theta 5 is less than the critical angle, so the light can escape at the end. So the light, in a sense, comes in here and gets bounced around, ricochets around here, it gets piped around and comes out the end. So the light can go from one side of the country, over mountains and into valleys. In a fiber optic cable, it can go around corners in a house, go into through walls into an internet box, and then get converted to your internet signal. So that's how fiber optics works, trapping light through critical angle. Beautiful application. So let me create a pause and give you a chance to write these notes down. All right, the next application is kind of fun, so I'm going to demonstrate. What I'm going to do is drop down out of view, and suppose I'm now behind a wall. I could see you if I take this device and lift it up, and I see you right now. If you were in class, I would be saying, hey, stop talking to that person. I would be saying things so you could see that you could tell that I could see you. And basically, you could see why, if I come closer with this device, this is what we call a periscope. There are two mirrors here and here, so the light comes in and then reflects here down the tube and reflects out. And so if I go like this, I could see you or the camera, and you could probably see my eyeball, because the light goes both ways. So that's a periscope. This is a crude model of a periscope, but in real life, they're used in a lot of things. One application is in a tank. This is a tank periscope. Unfortunately, it's kind of optically degrading. This should be clear, but you see this pattern here of reflector and reflector. So the light comes in here, ricochets up, and then ricochets. Why do they have these in tanks? Well, if you had a little peephole that you were looking out, snipers could shoot you. So you do this, and you look through this periscope just like this, right? And something like, let's see, maybe more like that. And you see it's pretty much the same device. And now if a sniper shoots this, they're just breaking some plastic that could be replaced. But it doesn't work with mirrors because mirrors can shatter. It works actually, this periscope, with total internal reflection. So what I'm going to do is change the camera and show you with this plastic block. This is basically like a part of this periscope. You see, essentially we can have like this, right? So you can see the top portion of it is this kind of triangle here along the top of the periscope. So how does that help us see around or light to take a corner like that, like you saw? Again, give me a moment to change the camera view. Now I want to show you how a block shaped like this could be used to redirect light in a periscope. But before I do that, I want to show you first the layout of my classroom. So right here we have the view of the chalkboard. I'm going to turn 90 degrees, and now you can see that 90 degrees away we have the exterior windows. I'll turn another 90 degrees, and you'll see the back of the classroom here. Note the air purifier on the counter, big white thing, and the orange bucket to the right of that. That's going to be useful for later. And then another 90 degrees, we have the wall that has the clock on it, and another 90 degrees, we've completed a full circle and we're at the chalkboard scene again. So, first thing that I'm going to do is take this piece of plastic to show you the windows over there. And before I do that, I just want to show you that there are no mirrors on this plastic. So here's this flat surface, no mirrors, and this hypotenuse, also no mirrors. So what I'm going to do is now have one flat end toward the windows and one flat end right up against the camera. And what you should see is that you can see the windows in this piece of plastic. It's not that great because the plastic has imperfections, but you can see the exterior windows through this plastic. Again, 90 degrees, exterior windows. So how did that happen? Let me use the laser pointer, so I'm going to turn out the lights to show you how the light was redirected in this plastic block. So give me a moment. So here's my block, and what I'm going to do is I'm going to take laser light and shine it in through the bottom, and it should emerge to the right. And here's with the red laser, looks pretty good. You could see the light coming from here, the bottom, hitting this bottom surface, and then exiting out to the right. I could try that with the green laser. Ooh, even better. So you see that light making that turn because of total internal reflection up on that hypotenuse of that piece of plastic. Okay, so there's the green one, and let's try the violet one. Ooh, that's really nice. So you see coming from the bottom, exiting out the right. I just got an idea. Maybe what I could do is shoot the chalkboard with total internal reflection. Oh, look at that. See the little dot? The blue dot doesn't look that good on the chalkboard. Let's try a different color. Let's try red or green. Oh, that's nice. Look at that. Right? I'm redirecting it with the plastic block total internal reflection, and red works pretty well. I think the green was the best in this case. All right, so that's how the block redirected the light through total internal reflection on this surface. Now I'm going to show you that this plastic block could be used to redirect light in another way, not just turning 90 degrees, but 180 degrees. Remember that if I turn 180 degrees, the back of the room has the air purifier, big white block, and the plastic Home Depot bucket, bright orange. So let me first cover up these edges with just some paper, because otherwise there are all kinds of optical effects that drown out this. This effect is pretty dim, so we need to block all the light. So all I'm doing is blocking light from coming in these two legs of the triangle. And what I'm going to do is put the hypotenuse up to the camera. And now you can see the back of the room. If I tilt around, there's the orange Home Depot bucket. Turn a little bit more, there's the big white air purifier. So you are seeing 180 degrees away through this plastic block. So let me again turn out the lights to show you how that redirection happened with, again, some laser light. So in the last demonstration, the light was redirected 180 degrees by coming in on the hypotenuse. Can we see that now with the laser pointers? So let's start with the red. I'll come in here on the right side. I don't know if you could see my hand, and you see two 90-degree turns of the light, total internal reflection twice on each of the legs of this triangle. So that looks really nice. And then let's try now. I think green is next. Oh, that shows up nice too. You see two internal reflections, and the light comes in from the right and goes out to the right, redirected. And the violet one, there, that looks really nice, really clear. Okay, again, I'm redirecting the light. And I could do this again, where this time I will shoot the light toward the back of the room, right, this way. I won't shoot into the camera because I don't want to mess up the camera, but I'll shoot it into the block. And do we see it on the board? Yes, we do. I see a purple dot. It doesn't show up that well on the camera, the purple. Let's try the red. Again, backwards and the block redirects it twice into the forward direction onto the chalkboard. There's our dot. And then, because I'm having so much fun here, I'm going to take the, oh, I did the blue light. Let's see the green. Oh, that's the red again. The green, okay. This should be nice. Oh, I see it in the air very nicely too. And there it is. That's the nice, really nice one. Okay, so that's how this block redirected twice and made a 180-degree turn with total internal reflection. So here's a diagram summarizing what we just saw in the demonstrations. You've got two optical triangles here, like plastic, joined with a rectangle in the middle. Light comes in here, strikes, and here it can come in, of course, not only because it comes in at 0 degrees, but because it comes from air to plastic, so we don't have internal reflection. But once it's in here, when it strikes here, this angle of incidence is greater than the critical angle for the air and the plastic, or whatever this is made of. And so we get 100% reflection down here, and then it comes down here. This angle right here, here's the normal, here's the normal, so this angle is also greater than the critical angle, 100% reflection. So if I'm standing right here, I could receive this light, which came from here. Maybe this is like a person I'm looking at, and I could see them through some kind of boundary. So there's theta 1, theta 2, both greater than theta critical. So 100% of the light reflects at both surfaces. So I'll create a pause to give you a chance to copy these notes down. All right, so that is the video for critical angle. So I hope you understood the physics. Remember that at the beginning, what's really on the Regents is primarily the calculation that we did at the start or earlier in the video, where you're calculating what the critical angle is for two materials. You use Snell's law, n1 sine theta 1 equals n2 sine theta 2, with the smaller index, air, or whatever the smaller index is, you put 90-degree angle. And in material 1, the higher index, the angle's unknown, and you solve for theta. That's the critical angle. So as simple as using Snell's law. Well, I hope you enjoyed that. I hope you enjoyed all the interesting, fun demonstrations today. I know I did. And I'll see you in the next physics video. Okay, sorry, I'm probably making this video over an hour long or something, but I'm having just way too much fun. I'm gonna put this green light right above the camera, and look, so my room must be dusty because we could see the beam so nicely. It goes around, strikes things, and really makes quite bright flashes. So almost like a science fiction movie. So look at that, okay? So I thought maybe you'd enjoy it too. All right, let's get back to work.